So some test-inspired warm-ups. Again, use your calculator. It's not cheating to use your calculator. It's knowing to use it especially when it asks you to. So number one is this weird-looking function, square root of the absolute value of x plus 4. And then which of the following are true? Well, continuous, differentiable, limit, asymptote, all of those things are real easy to see on a graph. They're not real easy to see based on this formula, but on a graph, they're pretty easy to see. So I think we should graph this thing. So grab a calculator. Second square root. Does anybody know where the absolute value key is in the calculator?
Math, number.
Yeah, math, number, and then the first option is abs, meaning absolute value. And if you have a newer calculator, at this point, it's probably most of them, it used to say abs and then put parentheses, now it puts the absolute value bars. X plus 4. And when I graph that, there's all these questions are about what's happening at negative 4, so I want to make sure my window includes negative 4. I don't know about y max and y min may not matter so much. As long as I can see what's going on at negative 4, now you can answer those questions. So I'm going to pause. Now we've reached sort of the calculus part of the question is it continuous? Is it differentiable? What's the limit? And is there a vertical asymptote? So I'm going to slow down a little bit and let you answer those. Yeah, it's continuous. Like I can draw it without lifting my pencil. So yes, it's continuous. Continuous doesn't matter what the shape really is. As long as you can draw it without lifting your pencil, we're good. It is continuous. Is it differentiable?
No.
Why not?
It's got a cusp.
It's got a cusp. So no, there's a cusp there. So not differentiable. What about the limit as x approaches negative 4? It does equal 0. So this is just worded funny. So statement 3 is false because the limit does in fact equal 0. And then statement 4, is that a vertical asymptote? No. No. Really, the point of the question is 1 and 2. These others are just kind of thrown in there. The difference between continuity and differentiability. It goes way, way back, but we're trying to start to mix in the review topics before we hit the review full time here next week. All right, number 2. Find the instantaneous rate of change of that weird looking thing. Well, since you're looking for it at a point, rather than take the derivative, which you could do, it would probably be easier to graph that thing and then let your calculator find the derivative. Because you got a second calc dy dx button. So put it in and then let your calculator find the derivative, whatever point you're looking at. That's not that graph, but that's how you would do it. So you want to press pause, type that in for the graph, and it's a weird looking graph, but that's okay. And then let your calculator find the derivative at x equals 2. Because it's a calculator problem, so you're not showing off. You don't have to prove that you know stuff. That you don't have to take the easy way out. They know that you've got a calculator. Use it. So there's my function: natural log of x squared minus 3 plus tangent of 3x minus 5x squared. The graph is weird, strange. And it's strange even with me having a strange window there. Second calc. dy dx is one of my options. You can scroll left and right, but you can also just type in the spot you want. So 2. So at x equals 2, dy dx is dy dx at x equals 2 is negative 12.746. And that's kind of all there is to that problem. But the point is, use your calculator rather than doing it by hand. I mean, you can do it by hand, and you can get negative 12.746 by hand. It just takes a while. There it is. Because I had to do divided by cosine and minus 20. And so you can get the right answer the long way or the easy way. So choose the easy way when possible. All right, number 3 is where we're going to spend most of the time today because it's a 3-part problem. So the first part is build, whoops, I also need to change this. X equals 0 is also one of the boundaries. So from x equals 0 to x equals 2, first job is find the area between those two curves. And again, you have your calculator, so if you need it to graph them, use it. Part B is it's a separate problem. You take that area and rotate it around y equals 2. Also, it's a write but do not evaluate, so you don't have to type it in the calculator. You can just write it out. And then part C is completely separate again. You start back with that region R, and you've got cross sections that are semicircles. So we're going to spend the bulk of the time. I'm going to hit pause so you folks at home can give it a try on this one. Maybe I should sketch the picture to get us all going in the right direction here. So I definitely don't want to go past 2. I know what y equals x squared looks like. So there's the job 1 is find that area. Part B is rotate that around y equals negative 2. And part C is build semicircles off of that coming up out of the page. A. So for part A, let's see, we're slicing dx slices. So we'll go from 0 to 2 of top minus bottom. So 0 to 2. The top one is x squared minus the bottom one is negative x dx. And some people type it in the calculator like that. Other people do the algebra on their own and make it x squared plus x. But whatever you do, you end up with 4.667. So that one was pretty straightforward, I think. Part B, we start getting complicated because we're going to rotate. So most people don't have a trouble drawing the picture, even understanding big R squared, little r squared. There's a washer. But finding big R and little r seems to be the issue here. So it's top minus bottom for big R. It's top minus bottom for little r. Question? So the top one is the x squared. The bottom one is y equals negative 2. And so that radius turns into x squared plus 2. Which, I guess if you step back, it makes sense because x squared is this, but we got to measure not to the axis. We got to go 2 more down. So it's whatever x squared is plus 2 more is the outside radius, the big R.
Go over that more.
Yeah. Let's go crazy zoom level here. So I want to find, you're good with this being big R, that label as big R, the outside radius. Mm-hmm. So I want to measure the top to the axis. Well, the top of that thing is x squared. That's the graph of x squared. The axis is just negative 2. Y equals negative 2. So the distance, it's a little bit related to what we did in this one, where top minus bottom. We're trying to get this height. I'm trying to get this height. Top minus bottom. X squared minus negative 2. And then for the little guy, same thing. It's the top one is negative x. I mean, not exactly the same thing, same process. Minus negative 2. So negative x plus 2. If you're not sure, if you're stuck, you can test different points. That you can test the endpoints. Because at this end, you know the big R should be 2 at this end. So if I plug in x equals 0, my big R is 2. I also know at this end, big R should be 6. So if I plug in x equals 2, I get R equals 6. So you can sort of spot check your R's to see that they make sense. Same thing with the little r. At this end, little r should be 2. So when x is 0, r is 2. Yep. At this end, little r is 0. So when x is 2, little r is 0. So if you're not sure about big R and little r, and that is the heart of the problem, the trickiest part of all of these, is check the endpoints and see if they make sense. I know you can take it from there. That's why we slow down from this part. So pi 0 to 2, big R squared minus little r squared. And this one said don't evaluate, so we're good with that. And I guess since it said don't evaluate, I would have been okay if you'd have just done r squared minus r squared. That would have been okay because we defined who big R and little r are. Again, that's kind of the easy part, so I'm not really worried about that. The key point is getting the two r's correct. All right, part C is building semicircles off of our original base area. So actually, I don't think I need to do another picture because I can just sort of visualize the semicircles coming up out of the page off of that initial area. So from 0 to 2, I'm going to add up the pi r squareds over 2. I'm adding up the semicircles. That means I need to figure out what r is. For each semicircle. And that's a little bit, it's not related to, I guess it's related, but it's not the same as one of these r's. Because what's easy to find is this diameter, but we need the radius. So I'll pause there and see if you can figure out how to come up with the radius. Once you get the radius, then you can plug it into this one. This one says find the volume, so don't just stop there. This is one where I want you to type it all in to make sure you can operate the calculator correctly. All right, so I like listening to you guys talk. You got to find the diameter first, because there's no way to directly find the radius, because it's half of that. So who knows? But the diameter would be top minus bottom, so x squared minus negative x, or x squared plus x, which means the radius would be half of that, x squared plus x over 2. And so how you take care of all the 2's and just all the 2's, I'm going to put the pi over 2 out front just to try to make my life a little bit easier, so that the only thing inside there is r squared, and r is x squared plus x over 2. And then type that in, although I'm going to show you, I'll look up our calculator here, because Apollo really did a nice job. He used all the fraction bars, and so it's really clear to see. Oh, it didn't put fraction. This is the right answer, but I wish it would have put fraction bars around this fraction.
It did when I put it in, but
parentheses.
I typed that in, but when I pressed enter, it just got rid of it.
Okay.
But yeah,
It just deleted them.
There should be
So-
parentheses around the smaller fraction that separate from pi.
Yeah,
and square.
it evaluated it that way, and you can kind of see that square doesn't go with that, so I changed my mind. I don't like how this looks. You put it in correctly, and you got the right answer. It just looks a little bit weird because your calculator did something funny.
Yeah. But yeah, you got it.
So I'm going to put it in just to make sure. I'm going to put it in with the pi over 2 out front. And then 0 to 2.
I did it that way. I thought it was parentheses.
So it just throws away, I don't know. I mean, you need them, and the calculator evaluates it with them, but x squared plus x. There it is. He's going to show me that.
Okay, yeah.
There it is. Looks good. And as soon as you press enter, the calculator says, I don't need those. That's weird. That is odd. Over 2 parentheses squared dx. Let's see if I got all the parentheses right. So the fraction bars do make it easier to see. But you can do it without the fraction bars. However you do it, you should land at 6.702. And obviously, if you have this clearly shown, but not the final answer, you're going to lose like 2 points, because that's not a big deal. But you do need to be able to put it in there correctly. Question on question C, or question 3, part A, B, and C. There is a section or a chunk on the test tomorrow that's laid out just like that. It's different graphs, different limits, whatever, different rotations and shapes. But find the area, rotate it around something, and then I use semicircles, but I think the one on the test is the equilateral triangles. But it's the same type process. So I wanted you to be able to handle one shape and doing like 3 different things with it. All right, number 4 is not really difficult if you know how to find the buttons on the calculator to find everything. This graph crosses the x-axis at one point between 0 and 1. What's the slope of the graph at the point? So let's use the calc 0 to find the point, and then we'll use calc dy dx to find the slope at the point. So put it in the calculator first, graph it, find the point it's talking about, and then find the slope at the point that it's talking about. Alright, so there it is. Y equals sine 2e to the x. Weird function. Weird graph. But sure enough, it crosses the x-axis once between 0 and 1. So second calc 0. Left bound. Right bound. Guess. So it crosses at 0.45. Now, answers need to be accurate to 3 decimal places, but since I'm going to use this number later, I probably want to carry more than 3 decimal places. 0.45, just to make sure my final answer is accurate to 3 decimal places. 45158.271. I mean, that's a little overkill, but if I stop it at 3, then my next answer might be only accurate to 2. And then if I use that again, it might only be accurate to 1. And so I need to be careful to carry that as best I can all the way through. And so I found the point. What is the slope of the graph at this point? So I want dy dx at x equals that thing. I'm not going to write it again. So second calc, dy dx will tell me the slope at, be careful, it looks like it's there, but that's not it. That's close, but that's not really it. So I need to And arrowing is never going to land exactly there. I'm going to need to type in 0.4515827. Again, that's probably overkill to get it accurate to 3 decimal places, but I know it'll be good to there. Negative 3.14159, that's sine. I mean, that's pi, but negative 3.142 is the slope at that point. So I don't know for sure that that's pi, but I'm guessing something happened where that turned out to be pi. But this is a decimal question on the calculated part of the test, so I don't need to worry about it. There's my answer. All right, again, you got 5 worksheets. 4 of them are due tomorrow. Remember, the back of the L'Hopital's worksheet counts as 2 worksheets because the review is on one side and L'Hopital's is on the other. I've posted answers to the review online, so you can find those. And so I think we'll be hopefully a little bit more ready than we were 50 minutes ago. Hopefully.